Okay, thank you. And thank you to the organizers for inviting me to this conference. And the theme of this talk is going to be the same as what Beatrice was talking about. And the theme is, before you start testing for deviations from GR, you better be very careful about what the predictions of GR are. And here I'll be talking about one very specific thing, but it's that. I mean, it's really having to do with making sure that we understand the true predictions of GR before we go about, finding deviations from that. So I'll be talking about the tidal deformation of compact objects. So it's mostly going to be about black holes, but I will be starting out with a more general context where, the object could be a compact object like a neutron star or a black hole. And the talk is based on two recent papers that go over all the technical details of what I'll be talking about here. So I'll launch right into it. So, I don't think I need to provide context for this. I think it was provided by earlier talks. So we live in this wonderful age of gravitational wave astronomy. And the issue here is about measuring the tidal deformation of compact bodies in gravitational waves. So let me launch right into it. So we have a binary system. So I have one reference body here that eventually will be a black hole, but for the moment could be a black hole or a neutron star. I have a companion body that's exerting a tidal field around the reference body. So we have this binary system. Of course, there's orbital motion, there's emission of gravitational waves, there's an in-spiral. But on top of this, I'm looking at the tidal field created by the companion body, creating a deformation of the reference body. And here I want to describe this tidal deformation in a neighborhood of the reference, excuse me, in a neighborhood of the reference body. And that neighborhood is going to be, is going to be assumed to be fairly small compared to the orbital separation. So the distance to anywhere within this region is going to be small compared with B. And the reason for doing that, I think, will become clear in the next slide. The idea is that I want to introduce a language where I can describe the tidal field in very generic terms as a Taylor expansion in powers of the small radius in that region over here, divided by the orbital separation B. The body zone is that neighborhood. So when I talk about the deformation of the gravitational field, I'm really talking about a description of the gravitational field that's limited to the body zone. And that's an idea that's very important for what follows. So as I said, the body zone is defined to be the region around the reference body up to a certain maximum distance that's assumed to be small compared to the orbital separation. One thing that I will also assume is that the orbital motion is fairly slow. So the separation here of scales comes or, is implied by the fact that I'm assuming that the orbital separation is large enough so that the orbital motion is fairly slow. I'm not necessarily assuming that it has to be very slow compared with the speed of light, for example, but that's an assumption that will come in later. But this assumption allows me to model the tides as a succession of static tidal fields. So the true tidal field, of course, is dynamical. It changes on an orbital timescale. But if that timescale is very small, very small compared to very large, I should say, compared with the internal timescale associated with the compact body, then I can assume that the time dependence of the tidal field is parametric, and I can model this as just a succession of tidal fields. And that's the regime of static tides. And of course, that's a limited context. That's a limited approximation. And Tanya had something to say about the limitations of this for really understanding the full aspects of the tidal dynamics in a binary system. But here I'll be happy to live in that regime. All right, let me start with a Newtonian description of this. And most of the talk is going to be about porting the Newtonian theory to general relativity. So in the Newtonian theory, well, it's the situation I described. And what I want to do is to take the potential, the Newtonian potential created by the companion mass, and I want to expand it in powers of R within the body zone divided by B, the orbital separation, assuming that the ratio is small. And the reason for this is that I want to introduce a very generic description of the tidal field that I can describe through a multiple decomposition. And I can go, as I go to, increasing order in that ratio, I can introduce more and more terms, and that sums up to a multiple expansion of the tidal field. Here, I'll be happy to truncate this to the leading order, which is quadrupole order, where the tidal field is scaling like r squared. So that's the scaling within the body zone. And it's also scaling with that curly E quantity here, which I would call the tidal quadrupole moment. And that scales like the mass of the companion, and it scales as 1 over, b the orbital separation cubed. And as you increase the terms, as you include more terms in a multiple expansion, you find that the multiple moments come with increasing powers of 1 over b. So if the orbital separation is fairly large, you do a pretty good job, even if you just truncate this to the quadrupole order. So the key point here is that the tidal potential created by the companion body, when you restrict yourself to the body zone, corresponds to something that grows in powers of r. If you want to now construct the full potential outside the deformed body, what you have to account for, in addition to the tidal field, and in addition to the spherical part of the body's potential, you have to account for the body's response to the tidal field. And that has to do with the fact that the tidal field is creating a pattern of forces on the body, and the body will respond to that perturbing force and will deform. And that deformation is described in terms of a decaying term in the body potential. The tidal field grows as r squared. The decaying term goes as 1 over r cubed. It scales with 5 powers of the body radius. And in addition to that, there's a number in front that's dimensionless and captures all of the details of the body's internal structure. So the equation of state and all of this information really tells you how much deformation you will get for a given tidal field. And all of those details are incorporated into this love number K2. 2 is for quadrupole order. There would be more love numbers as you increase the multiple expansion. So in Newtonian theory, all of this is very simple. And what you see emerging for the potential outside the body is basically growing terms that describe the tidal field itself, decaying terms that describe the response. And in both cases, we're talking about elementary solutions to Laplace's equation. And you can make a one-to-one correspondence between the love numbers that occur here and multiple moments of the mass distribution. So the body would be spherical in isolation, so all of its multiple moments would be 0. But as you start deforming them because of the tidal forces, you start generating non-zero multiple moments. And at leading order, you would have a quadrupole moment for the mass distribution that would be proportional to K2, the love number, r to the 5th power, and would be proportional to the applied tidal field. So the response is linear in the tidal field, at least within this approximate description here. There could be nonlinear effects coming from the fluid mechanics inside the body, and I'll mention a couple of words about this later on. The key point here is that in the Newtonian theory, everything is simple, and there is indeed a one-to-one correspondence between love numbers and tidally induced multiple moments. And this correspondence is very immediate in Newtonian theory, and the main aspect of the talk, the main theme of the talk, is going to be about the fact that there's nothing natural nor direct about this relationship here if you're working in general relativity. So we'll get to that in a moment. Okay, so, well, we'll get to that right now. So what can you do to port all of this to general relativity? Well, the first thing that I'll say is that it's very straightforward to generalize this slide here from Newtonian physics to relativistic physics. Instead of solving, the Newtonian field equations, you solve the Einstein field equations, but the ideas are exactly the same. You take your reference body, you look at the tidal field in a neighborhood of it that's assumed to be small compared to the orbital separation, You introduce a growing term in the metric that corresponds to the tidal field, and you include decaying terms that will describe the response of the body to that tidal field in full GR. And here I'm working to linear order in the tidal field, so I'm doing perturbation theory around the Schwarzschild metric that would be describing the body in isolation. So it's very straightforward to promote the Newtonian potential U to the full metric of a tidally deformed body. And here I'm just showing you, the TT component of the metric, which is the one that's that's closely analogous to the Newtonian potential, but all components could be worked out. And without the perturbation, you would get the well-known Schwarzschild form for the metric. And as you include the first order metric correction coming from the tidal field, you would find a growing term that describes the tidal field itself. You would find a decaying term like this that describes the response to the tidal field. And in front of this, you would insert a K2 that would now measure the tidal response of the body in full GR. Now in GR, of course, the precise description of all of this is a bit more complicated. And while A happens to be simple, but if we were to look at higher multiple orders, it would be slightly more complicated. B turns out to be rather complicated. It's a complicated function of R, including a log term that has this as an argument. But if you take this and expand it in powers of m over r, if you wanted to recover the Newtonian description, you would find that while both A and B start out as 1 plus, well, in the case of B, plus corrections of order m over r squared, and all of this. So exactly the same structure emerges. But now you're working in full GR, and you've computed your K2 depending on the details of your body inside here. You've computed your K2 in full GR. So at this stage, I can claim that K2 is a property of the deformed metric. The deformed metric is defined in the body zone and only in the body zone. And all I can say about K2 is that it's a property of that metric. I can say even more. It's a gauge invariant property of that metric. And I cannot say more than that. A priori, I cannot say anything more than that. And I cannot say that this K2 will eventually show up in gravitational waves in a form where it can be measured, something that Tanya yesterday talked about. And the rest of the talk is about making that gap, bridging that gap between a K2 that's just a property of a deformed metric in a neighborhood around the reference body, and something that you would observe at infinity in gravitational waves. The other thing that I wanted to say is that while this construction here applies to black holes and it applies to neutron stars, if you apply this to a neutron star, what you have to do is to take your vacuum solution, the one that I'm displayed here, and you have to continue it to the interior of the body. And it's that matching with the internal solution, the interior solution, that would determine what K2 needs to be for any given model of a neutron star. So that's how you do the calculation. You take the vacuum perturbation and you match it to the interior perturbation, and the matching will determine that unknown parameter K2 for a given model of a neutron star. If you're doing it for a black hole, well, there's no interior, so you're already done, but you would want the metric to be well behaved and smooth across the event horizon. And the log term here is preventing that. So in order to get something that's well behaved for a black hole, you actually have to kill that term that would give you unsmooth behavior across the event horizon. And the way to do that is to kill the K2 parameter. And that's the origin of the result that love numbers vanish for black holes. All right, so that's what you can do in terms of porting in results to general relativity. Before I move on, any questions about any of this at this stage? Okay, I'm hearing none. So let's move on. Now, it turns out that there's a bit of fine print in everything that I've talked about at this stage. And the fine print was basically made bigger by Sam Gralla in a paper from several years ago. And what he observed is that, well, here, when I describe my metric perturbation in this way, I made a choice for what I call a growing solution to the perturbation equations. And I made a choice for what I call the decaying part of the perturbation. The growing part, I said, is the tidal field. The decaying part is the response. But what Sam pointed out is that, well, the property of growing is not going to be spoiled if you add a little bit of the B into the A. So what Sam pointed out is that if you make a redefinition of your basis functions and add a little bit of B into the A, you're not changing the fact that you're still dealing with a growing solution. The decaying solution has to remain decaying. So you don't have a freedom to redefine B, but you have a freedom here to redefine A in this way. And if you were to do this, then you would change the characterization of what is a tidal field and what is a response. And that is a very simple calculation, would lead to a shift in love number. So depending on what you choose for that scaling parameter over here, something that has the dimension of length, you would find that the K2 that was properly assigned under the previous choice of basis functions, if you make this redefinition, the K2 would be reassigned to something different. So in a different basis, love numbers for black holes would not be 0, they would be -12 or whatever the number turns out to be. So that told us, and that is something that I learned from Sam, it told us that, well, love numbers are not sacred things. I mean, you can redefine them at will according to this prescription over here. And if you're going to assign operational value or measurable consequences to a love number, you have to account for possibly this ambiguity that redefinitions could affect the numerical value that you assign to a love number for any given object.
So just can I ask one quick clarification? This A and B is not constrained from the equation of motion?
So the field equations give you two classes of solutions, one growing and one decaying. But they're linearly independent. So you can always throw one into another, the other one into the other, and you're not changing the fact that they're also solutions. So we have two linearly independent solutions to the perturbation equation.
Right, but you are redefining containing a R itself. It's a R.
Oh yeah, no. So the solution is actually R squared times A, and it's actually 1 over R cubed times B. So those are the real solutions. Right. So what I'm saying is that this individually are both solutions. And because I'm working in linear perturbation theory, I can always add solutions and they remain solutions.
Okay,
yeah, thanks for the clarification. That's good. So the point is that, I declare that love numbers are 0 for black holes, but that's true under one, definition for the basis functions. And if I make a redefinition, then I change the assigned number to the love number. And to me, that's and to Sam as well, that was a strong hint that maybe there's something more that needs to be said about love numbers before they get incorporated into gravitational wave models that incorporate tidal deformations. And to me, that made the point really clear that the love number by itself may be a property of a deformed metric, but it's not yet a property of a gravitational wave model or a gravitational wave signal. You have to bridge that gap between information about the immediate neighborhood of the body and what you actually measure at infinity. All right, so how do we bridge that gap? How do you turn the love number into something that's really observable? For example, a parameter that would enter equations of motion for the binary system, and a parameter that would eventually be fed into a wave generation calculation and give you, a model for the gravitational waves emitted by this binary system that includes information about tidal deformation. So to me, that was the central question all along, and it seemed to me that in the literature and in for a lot of people that, well, this was an answer, that was a question that need to be posed, and a question for which we already had an answer. And the answer was in fact provided by Newtonian theory. So Newtonian theory makes a very direct, relationship between the quadrupole moment that corresponds to the tidal deformation of the body and the Love number, why not continue to apply this to GR? And the answer is something that Beatrice talked about in her talk. The answer comes from the fact that even though Love numbers can be defined properly and completely, rigorously in GR, at least in this context, individual tidally induced multiple moments for bodies in a binary system are not defined in GR. There's no GR intrinsic definition for these things. These are the things that would show up in equations of motion. These are the things that would show up in a waveform model. But before you can put them there, you have to define them. You have to give them a definition that's appropriate and rooted in GR. And I claim that until recently, this was not done. It was taken for granted. It was not done properly. The key thing is that we need a notion of multiple moments for individual objects in a dynamical space-time. And therefore, we're not working under the conditions that Beatrice described, where we were dealing, where if you want to apply the algorithm that was provided by Garrosh and Hansen, you have to start with a stationary space-time, and then you go to asymptotic infinity, and you can derive everything there. Here you have, none of that. So I'll develop that question. I'll develop that theme quite a bit in the next few slides. But before I do that, I'll just tell you that while it didn't stop people, that lack of definition for multiple moments of tidally deformed bodies in GR, that didn't stop people from actually, doing calculations with these things. So what I'm trying to say here is that there was a prescription that was introduced in the literature to actually make those multiple moments defined. And I just want to take the time to argue that this prescription is ambiguous and not adequate. It's not good enough. The prescription was this. Okay, so we go back to the metric perturbation. We notice a growing term. We notice a decaying term. If only we could get rid of the growing term, we would get a metric that is nice and asymptotically flat, and a metric that seems to correspond to an object with multiple moments. So this was the idea, and the idea was a subtraction prescription where you just subtract out the tidal field, and I'm putting the tidal field in quotation marks for a reason that will become clear in just a second. You just subtract it out from the perturb metric. You're left over with a metric that is now asymptotically flat. And in this approach where we're thinking of the tides as a static, as a succession of static configurations, we do have a stationary spacetime that's also asymptotically flat. And we do then have access to the Garrosh-Hansen prescription to calculate multiple moments. Problem solved. We have our multiple moments. Well, problem is not solved because the prescription is actually ambiguous for essentially the same reasons that were pointed out by Sam. I mean, the focus of the discussion is slightly different, but the question is, what is the tidal field? Well, the answer would be the growing part of the perturbation. But what is the growing part? Is it the one that I called so in my original slide, or is it the redefined one according to Sam? And the point is that you don't know. There's no way to tell. There's no such thing as the tidal field. There's such a thing as the total metric around the deformed body, but there's no meaningful decomposition of that total metric into a tidal field and a response. They come together. So any attempt to subtract anything would be based on your personal choice that you may really like of a definition for a tidal field, but somebody like Sam could come in and say, well, I prefer this one. And the point is that all your multiple moments would become dependent on that scaling parameter, and they would all be ambiguous in the same way that the Love numbers were ambiguous before. So that doesn't work. And it's also not working because, well, maybe you would like to go beyond linearized perturbation theory. The subtraction prescription works really well if you have a linearized perturbations that can be decomposed into linearly independent solutions. That's the typical situation. But if you go beyond linear order, and why not, then there's no superposition of solutions anymore. So you cannot subtract out a solution from the solution. It doesn't work like this anymore beyond linearized perturbation theory. So that prescription cannot be, cannot be the true story. And then, the Garrosh-Hansen moments would not allow you to actually go beyond the static tides approximation to actually account for time changes in the tidal environment. So that really doesn't work. So I wanted something better. And here's what I proposed. And that was the first paper that I talked about, that I mentioned in the introduction on the first slide. So here's the prescription. The prescription is rooted in post-Newtonian theory. And for me, that's the price of entry. So I'm going to consider that to be an essential, an essential input. And the input is appropriate when the mutual gravity between my two bodies is weak. The black hole will have very strong internal gravity. The neutron star will have very strong internal gravity. I'm not giving up on that. I'm just saying that the mutual gravity between the black hole and the companion is going to be weak. And that, is fine because that goes well with my initial assumption that the orbital separation was large, and it works well with the assumption that the tidal field was changing slowly. So all of this corresponds to an assumption of weak mutual gravity. So I don't consider that to be, losing too much in terms of physical reach, but I consider that instead to be very general, but it is, very natural, but it's a very essential assumption for everything I'm going to be doing. All right. So the idea is that I want to construct the field around the body in full GR because post-Newtonian theory is not applicable if I'm too close to the body. But I want to construct a metric that describes the weak mutual gravity between the companions in a post-Newtonian way. So that requires the refinement of my zones over here. I still have the body zone where I get my full tidal metric. Now I introduce a post-Newtonian zone, which is going to be the place where gravity is weak enough for that assumption to be valid. And that post-Newtonian zone is not allowed to go too close to the body because gravity becomes strong there. So the post-Newtonian zone will be excluding this blue region here that I call, the exclusion zone. So when I do my post-Newtonian theory, I'm working not everywhere. I'm working around the body, outside of that blue region. It's going to be very important for, the technical aspects of this, that there's an overlap between the post-Newtonian zone and the body zone. Because what I'm going to be doing here is to use post-Newtonian theory to construct a metric everywhere outside the blue region. And I already have my tidally deformed metric for the strong, gravity body over here up to the body zone. Two alternative descriptions of the same gravitational field, they can be matched up in this region here where both are valid. So information that I don't have here and information that I don't have here can be obtained by matching the metric back and forth. So it's in this overlap region. So it's a game of matched asymptotic expansions. Okay, so very briefly, how do I do my post-Newtonian theory? Well, the way it's done is that you reformulate the Einstein field equations completely exactly without approximation first through this Landau-Lifshitz version where the main variable is no longer the metric, but it's this Gothic metric here that involves the inverse metric and the determinant of the metric. So that becomes the main variable. You can, and you do, impose a coordinate condition on the metric that's known as harmonic coordinates. And once you have that, you reformulate the field equations, and they will look like wave equations on top of flat space for that metric variable. And everything that's nonlinear, and there's a ton of stuff that's nonlinear in the field equations, will be lumped in this quantity here, which is an effective energy momentum pseudo tensor for the metric variable. Typically, this would be constructed for matter, but I'm working in the space between objects, so there's no matter to be found. So it's mostly constructed, or it's entirely constructed from the field, and it involves field derivatives to all orders, so it's a mess. Now, the point is that when I solve those equations and I work in the near zone, well, the dominant part of the field equations comes from this Laplacian stuff. And the way this is done in practice is that, well, you start with flat space, you put flat space as a solution on the right-hand side, you iterate the equation once, you get your first order correction. You take that solution, you put it back on the right-hand side, you iterate again, and you keep doing this until you reach the level of accuracy that you want. And formally speaking, this is an expansion in powers of g. It's an expansion in powers of 1 over c squared. And you just keep that to, you keep cranking them out until you're satisfied. Typically, you would be doing this everywhere. You would not have an exclusion zone. So what you have to do here is to truncate your domain of integration to be outside of the exclusion zone, but your solution outside the exclusion zone still has to have information that pertains to what lives inside. And the way that you incorporate this information is through homogeneous solutions to that Laplace type equation. So if you're working in a near zone, the time derivatives become less important. So it really becomes a Poisson type equation with a known source, a source that you've constructed from the previous iteration. So at every stage of every iteration, you're really solving a Poisson type equation. And if you want to incorporate information about the exclusion zone, you have to do it through solutions to the homogeneous equation, which are Laplace's equations. And Laplace's equations, well, they will come with decaying solutions that will have a one-to-one correspondence with multiple moments. So that's how the multiple moments get defined in this context where we're working in the post-Newtonian regime for the mutual gravity. We solve the post-Newtonian equations outside of the exclusion zone, and we incorporate information about the exclusion zones through a succession of decaying solutions to Laplace's equation that come with multiple moments. So when you look at the situation safely here outside the, inside the post-Newtonian zone, the body over here will appear like a point particle with a multiple structure. There's nothing point-like in the space-time, but as you look at it far away, you do see this multiple structure emerging, and it's as if you're dealing with a point particle with all of that multiple structure. This is the way that I can define multiple moments for a body in a fully dynamical space-time where everything moves and we don't have asymptotic flatness and we don't have stationarity. That's how I will define multiple moments for a tidally deformed body through this post-Newtonian matching strategy where I take the metric in my body zone, I take the metric in the post-Newtonian zone, and I match it in the overlap region, and I determine all of this unknown multiple structure that had to be introduced in the post-Newtonian space-time. That is how you can relate two worlds: the fully relativistic world that gave you the love number in the body zone, and the post-Newtonian world where you can define multiple moments. And the very careful matching that you do in the overlap gives you the relationship between what lives in the relativistic world and what lives in the post-Newtonian world. So I was able to carry out this matching calculation to 1 PN order, which is limited, but enough to really reveal the essential aspects of this. I was able to do the calculation, including time derivatives of the tidal environment, so beyond the static description. And I was able to do the calculation beyond linearized perturbation theory by also accounting for quadratic terms in the tidal potential, in the tidal field. So it's a bit of a mess of a calculation, but the important aspect of this is that the relationship that we had in Newtonian theory is now emerging, but it's emerging with a very different interpretation where the K2 is fully relativistic and the multiple moment, the quadruple moment here, is defined in this post-Newtonian way in a proper way in this dynamical space-time. So that relationship that was taken for granted previously has now been derived, I would say, appropriately in GR, and that required providing an adequate definition for what the multiple moments had to be, and that's where the post-Newtonian story comes in. I believe there was a question.
Yeah, I just wanted to quick clarification. So the regions are changing dynamically.
Yep.
There's blue region, for example, which you incorporate in calculating the multiple moments. That region is also changing dynamically.
Yeah, so if I view this in the common rest mass frame of the binary system, then yes, that blue region is moving around. Part of the technical details is to actually move to the rest frame of the reference body. And what that means is that everything else is going to be moving around around the reference body. But yeah, everything is changing with time here.
So post-Newtonian zone is also getting redefined with the time scale. It is changing, and that's not that doesn't pose any problem.
No, because in fact, so the boundary of the post-Newtonian zone really depends on how strong gravity is at the boundary, and if you're working in that frame where the body is at rest, then that in fact is a static thing. So there's no time dependence in the size of that boundary.
Yeah.
Does that answer your question?
Yeah. Thank you.
Excuse me, I have a question too. Yeah, so in your calculation, when you are matching the exclusion zone with the post-Newtonian zone, so there should be a dependence on the choice of radius. So there should be an extra parameter, right? So the ambiguity still remains, right?
No, there's no ambiguity, because and here I have to refer to the technology of match asymptotic expansions. So the point is that you're not matching at one radius, you're matching across a finite region for all radii within that region. So the exact place where you put this boundary, the exact place where you put that boundary is irrelevant so long as one is inside the other. But what really matters is that there's a finite region where you do the matching, and you do the matching everywhere in that region.
Okay, thank you.
Okay, so I'm slowly running out of time, so I think the rest of the story will be fairly quick. The question is, okay, so I worked this out to 1p order, and I was very proud of myself, and I could reveal the relationship between a fully GR calculated love number for a neutron star and the tidally induced quadrupole moment for that neutron star. And now, can I just go ahead and take this to a black hole and say that, well, K2 is 0 for a black hole, therefore this is 0 for a black hole? And the answer is that I can't. The reason why I cannot is because so far, and in the scope of this calculation, this multiple moment was calculated through 1pn order. When I did the PN calculation, the scaling of R was immaterial. R did not affect the post-Newtonian scaling of my quantities. R could be assumed to be very large, R could be assumed to be small. That didn't affect the post-Newtonian scaling of my, of any quantity. But if I want to apply this for a black hole, R is no longer independent. R is now tied to the mass, and to each power of m, I have to assign a new post-Newtonian order. So the right-hand side of that equation, if I wanted to apply it to a black hole, would be of 5pn order, because I have 5 powers of the mass over here. In order to match a 5pn right-hand side, I would have to define and calculate a quadrupole moment to 5pn order. And that's beyond me, and I believe it's beyond the state of the art in post-Newtonian theory at this stage. And that made me very upset, because I didn't see how to resolve this issue. What is the Q for a black hole, given that K2 might be defined to be 0? What is that relationship for a black hole, when the relationship really relies on a post-Newtonian expansion carried out to 5pn orders? So very upset about this, and I was thinking about, how could I possibly resolve this without the need to go to 5pn orders? And the answer came to me in some flash of inspiration at some point, although it took a long time. And the answer turned out to be, well, don't do it at 5pn orders, do it at all pn orders. And that's what I did. And that sounds a little bit strange and crazy, and it's going to sound even more strange and crazy as I start explaining things, but bear with me. So the reason why those calculations are difficult, even at 1pn order, is because everything is dynamical. Everything is moving with time. You have to account for all of this, and it's a mess. What if I could have a static binary? Then all of this dynamic stuff would go away. I would have a true static tidal environment, and maybe I could do the calculation much easier. And the answer is true. It's true. How do I have a static binary? Obviously, it doesn't make any sense, but I can arrange for a static binary if I give my black hole a tiny amount of charge. That's what I call big Q. And I put another body around it with a massive amount of charge. If I arrange for the charge to mass ratio here to be the inverse of the charge to mass ratio here, I can balance out gravitational attraction and electrostatic repulsion and really get myself a nice static binary system. Now, the price for that, of course, is the addition of charge, but keep in mind that the amount of charge I add to the black hole here can be really small. It's just that I need to compensate by this by giving that body a huge amount of charge, and that means that this companion here cannot be a black hole because Q over M for that guy is going to be huge, so it cannot be a black hole. The Q over M here will be assumed to be tiny. But the point is that I can arrange for a nice static environment, static tidal field, a nice static binary system by using this device. I will argue later that adding a tiny amount of charge to the black hole is not going to change its properties very much. So maybe the price to pay is not that high given the immense benefit of having this static spacetime. Now, on top of this, I'm going to assume that this body is really far away, and in fact, I'm going to assume that this body itself is tiny, and I'm going to calculate the gravitational field around the big body as a perturbation of Reissner-Nordström. So instead of going back to the post-Newtonian picture, here I'm embracing the full GR aspects of this, and I'm saying that this new static binary here is going to be calculated as a perturbation of the Reissner-Nordström spacetime. It's still going to be linearized perturbation theory in GR, but now it's carried out to all orders in post-Newtonian theory because I no longer need to assume that the separation here is large. So that's, the setup. I'll spare you the details, and I'm running out of time anyway. But what I can do is this. I calculate the metric everywhere in my spacetime as a perturbation of Reissner-Nordström. Then I do all the technical things that will allow me to return to the post-Newtonian picture. And I incorporate, for example, a conversion to harmonic coordinates. And I can then incorporate an approximation where the separation between the big black hole and a small body is large. And I can reintroduce after the fact the post-Newtonian expansion. And with that, I can read off the multiple moments because remember, my multiple moments here are defined in post-Newtonian theory. So by starting with the static binary and doing the calculation this way, I can recover the multiple moments in a post-Newtonian expansion that now I can carry off to all orders. And the final result of this, and that's the punchline, is that for my static binary with my charged black hole, all tidally induced multiple moments for that black hole vanish, and they vanish to all post-Newtonian orders. So that for me resolves the question. So I could not apply this relation to a black hole because of the reasons I explained, but it turns out to be true, at least for this contrived situation, and I'm not shying away from the fact that this is a very contrived situation. At least for that situation, Q turns out to be 0. Now, here's where I think the calculation really comes in its full power. I'm claiming that all the idealizations that I made in this very contrived situation don't matter all that much. The first thing that I think you should worry about, and certainly the thing that I worried about, is, well, okay, I derived the relationship between Q and E for a very contrived situation involving a very specific tidal field that has nothing to do with what a real astrophysical environment would provide. So the E that I provide here was very contrived, and the Q was 0. I claim that this relationship between Q and E, if you could carry it out to full glory in 5PN, would be generic. Doesn't matter what E is, Q will always be proportional to it. So Q for a contrived environment will be in the same relation as Q for a natural, astrophysically well-motivated environment. If Q is 0 for one, it's going to be 0 for the other. So I claim that Q being 0 is not a feature of the contrived, binary system. It's actually a feature of the black hole. So it will apply to any tidal environment. It's an argument, it's not a proof. Maybe you're upset that, I went back to a strictly static limit instead of just arguing that, well, it's a succession of, static configurations in a slow tide type expansion, but I'm not bothered with this because the static limit in all calculations that were done previously really captures the leading term in an expansion that you might carry out in this ratio here, which is assumed to be small, internal time scale divided by orbital period. So I work strictly in the static limit, but I claim that this would capture, if I could do the dynamical calculation, I claim that when this ratio is small, the static result would capture that. And well, maybe you're bothered with the charge, but then as I argued before, this charge can be tiny. It doesn't, it cannot be 0 because I need to balance out my forces, but Q can be very, very small. The charge to mass ratio can be as small as I want it to be. And therefore I'm not changing the properties of the black hole in a very essential way. So I would claim that, if I could take the limit where Q goes to 0, I would still have a vanishing, tidally induced multiple moments for my black hole. Again, it's an argument, it's not a proof, but at least it convinced me that the vanishing love number of a black hole could actually be tied to something which is not by itself directly observable, but something that can be made observable. Those tidally induced multiple moments can be made observable by putting them into equations of motion in post-Newtonian theory, as was done, and putting them in gravitational wave models, as was done, but now in a way where it's a lot better controlled and a lot better tied with strong field gravity. So I'll flash my conclusion, and I think I'll stop here, and we can discuss if you wish.
Thanks, Eric, for the wonderful talk. And now floor is open for questions. So if anyone has any questions, please go ahead.
I would like to ask.
Hello?
Please
go ahead.
Thank you, sir, for a wonderful talk. My question is just simply this, that by adding the charges, you might say that the charges are very small. That is, the charge on the capital Q may be small, but its effect in tidal deformation of the body is not small. So that means I'm just wondering whether you're not artificially introducing some extra deformation, which may not necessarily belong to the deformation caused by the gravitational. I'm just wondering whether there is something that is being put in which may not actually belong there.
Right. So you're certainly right to say that the adding the charge to the black hole is changing the curly E by quite something. So you're changing the tidal environment by quite a lot. So your question really ties to this point over here. So to me, I can give an argument that if you believe that the relationship between Q and E is generic, it doesn't matter whether the tidal environment is extremely contrived in the way that I conceived here, or it's very natural, the relationship will turn out to be the same. And if Q is 0 for one, it's going to be 0 for the other one. Now, it's an argument. It's a plausibility thing. I consider that to be plausible, but it's not a proof. So there could be loopholes in this that would tell you that, yes, you're correct, that there are some limitations to this. And in fact, the real Q for a real black hole in a real tidal environment might turn out to be very different from the 0 result that I claim here. Could be. I don't have, a completely, I don't have an answer to that. I mean, I'm sort of speculating to some extent, but I consider the genericity of this relationship to be pretty plausible. And I'm willing to put some money on that. So I'm fairly confident that this will turn out to be true. But I agree that, you know, only a full analysis carried out to all required Post-Newtonian orders would actually resolve the matter once and for all.
Niash, please go
ahead. Hi, Eric. Very nice. I'm glad someone else is up here on this side of the Atlantic. So it's very interesting. I guess the question that I have is, I mean, it's not just the gravitational tidal forces. You have the electric tidal, I guess, tidal fields. So if you do have the charge, so why are you then focusing on just the gravitational one when you turn on the electric field as well? So it seems that you're constraining a combination of, I guess, electromagnetic tidal deformability and gravitational one.
Right. So I focused on this because I happen to be interested in that. So when I do the calculation, of course, I have to calculate the full perturbation to the vector potential for the EM field that's coupled to the gravitational perturbation. So all of those details are included. Now, in principle, from the perturbed vector potential, I could come up with tidally induced multiple moments for the charge distribution, and I could calculate this. It's just that in this case, I don't quite know what to do. I don't know how to define those multiple moments. I'm sure some definition could be provided, and you know, I could do the calculation, but I just didn't know what to do with this, so I decided not to worry about it.
I guess my worry is that there's some cancellation between the electric, I guess, tidal deformability and the gravitational one, which if you move away from this, I guess, static limit that you're looking at, that cancellation is not going to be perfect anymore.
So I don't think there would be a cancellation, because we're talking about multiple moments for mass distribution on the one hand and for a charge distribution on the other hand. So I think they're really different things. But I think it goes back to that statement over here. So if you find that less plausible than I do, then that might be one way in which, you know, that doubt would be seeping in.
Okay, thanks.
go ahead.
Hi, Eric. Nice talk. I was wondering regarding your conjecture on how this may get extended to neutral black hole binaries. Phenomenologically, it should be possible to verify that, right? With or is it not, with numerical relativity waveforms? Whether indeed black holes, neutral black holes, also have a vanishing love number, tidal love number.
Yeah, so the issue is the love numbers, there's no issue. So love numbers, if you take one, you know, particular definition of the perturbation functions, then the love number, the numerical value of love numbers can be calculated, and there's really no issue. The issue is really to communicate this to so multiple moments for tidally deformed bodies. And it's certainly conceivable that you could do this from numerical spacetimes. You could, you know, numerically evolve your space-time and maybe consider an early regime where, you know, the orbital separation is large enough, and then you could come up with some construction that would go from your numerical simulation to, for example, my definition of multiple moment, and maybe you could show that this is zero. So it's conceivable you could do this. I'm not sure of the practicalities. I'm not sure of numerical accuracy and all of this. It's high to do numerical relativity at large separations. Maybe the numerical constructions, you know, if you're aiming for zero, you'll never get zero. So I mean, there are practical issues, but yeah, I think there are other ways of doing this, and my definition of multiple moments is not unique. I mean, there was a suggestion before that you could use a self-force type formalism to define multiple moments, and you could do it like that as well. So I'm not claiming that this is a unique, but I'm claiming that this is at least unambiguous, that it gives you a very, you know, solid prescription to go from love numbers to multiple moments, especially when you're modeling your waveforms in a way that's coming, or at least strongly inspired from Post-Newtonian theory, which is the way it's done. I mean, the way that people calculate templates is to start from Post-Newtonian and add terms that are motivated from post-Newtonian theory. And then you can do all sorts of corrections to that, in a EOB type way. But I think, this whole approach is really grounded in post-Newtonian theory. So that's why I think here it makes sense to ground everything in post-Newtonian theory. But I'll admit that it's not a unique way of approaching the problem. I think I probably went on more than you wanted.
No,
and I'm not sure I answered your question.
You did, but if I can sneak in a quick second question.
Yeah, sure.
Okay, I'm not sure whether you were there at Michelle Levy's talk yesterday, but she mentioned finding these spin love numbers at 5 p.m. In the effective field theory approach. Are you aware of those? And if do you see them emerging in post-Newtonian theory done in a So there are two classes of love numbers. The ones that I talked about are associated with mass distribution. There's also the ones associated with velocity distribution. So those are, you can call them spin love numbers if you wanted to, but that's just a name. Yeah, so there are two classes of love numbers, and the one that dominates is really K2. So that's the one that really shows up first when you start incorporating tidal information in waveforms and such. But in principle, they're all there. So in principle, they're related to the electric and magnetic parts of the wild tensor, right? So
yep.
Yeah, okay.
That's right. So two types of tidal fields, electric, magnetic, and therefore two types of love numbers. One having to do with the electric type tidal field, the other one with the magnetic type.
Yeah, the way she presented it, maybe I'm mistaken, but it seems something novel and different. But if it is the same thing, then I understand. Yeah.
Okay, I cannot say because I didn't hear the talk.
Fine. Thanks.